So we've practiced comparing graphs for linear, quadratics, and for exponential. And most of the time you can make a quick graph and you're going to be able to tell what's happening without having to go through and break down the table. But that's not always the case. So in this exercise, we're going to practice, what if I just have a table and I don't have enough information to really help me out unless I complete what I've been working with. So remember, linear tables, they have a constant and what we call a first difference. So if I was to look here, everything on the x is going up by 1, right? So since everything on the x is going up by 1, I'm not going to panic too much about the side. I'm like, okay, they're good. I'm going to focus on the y. And the y values, I'm at negative 15 and now I'm going to negative 18. Well, how do I get from negative 15 to negative 18? I subtract 3. How do I get from negative 18 to negative 21? I subtract 3. Negative 21 to negative 24, subtract 3. So as you can see, what's happening here is we have a constant first difference. The first time I looked for what's happening between my y's, they all said we're subtracting 3 every single time. We found the pattern. So in this particular case, we'd say this is a linear. This is a linear table. Okay, so now let's look at a quadratic table. And I'm going to call this U formation. And the reason I do that is because if I was just to look at this graph or this table and I was to graph it, like, well, if I was going to graph this, you know, negative 3, 9, 1, 2, 3, and you can just kind of get an idea that just looking at the points, this was easily going to make a U. So you'd be like, yeah, that's a parabola. That's a quadratic. Because the table is centered around the vertex. And it would be nice if they always looked that way, but they don't. So we need a system for what if they don't center the table around the vertex. So the first thing I did here is, remember in linear how we use the first difference? We still use differences. We just don't use the first difference anymore. So how do I get from 9 to 1? Well, I subtract 8, right? How do I get from 1 to 1? Well, I don't do anything. It's still 0. How do I get from 1 to 9? I add 8. This is my first difference. For quadratics, we can use the second difference. How do I get from negative 8 to 0? I add 8. How do I get from 0 to 8? I add 8. So if my second difference is constant, I know I have a quadratic. So let's look at that when they haven't given us the vertex in the table. So here I have a new table, 2, negative 4, 3, negative 9, 4, negative 16, 5, negative 25, and 6, negative 36. And what I need to do here is I'm going to go ahead and check out those differences because it's not around a vertex. Now hopefully maybe you notice that 2 squared could be 4, so you're thinking about that would be that other side. So let's try it out. First difference first. I'm going to work on the first one. If I'm at negative 5 and I want to get to negative 9, subtract 5. If I'm at negative 9 and I want to get to negative 16, I subtract 7. Negative 16 to negative 25, subtract 9, and from negative 25 to negative 36, I subtract 11. That is not a constant. So right there I know, not linear. Then I go ahead and move to my next set. Now I'm on my second difference. Negative 5 to negative 7, I subtract 2. Negative 7 to negative 9, subtract 2. Negative 9 to negative 11, subtract 2. What I have here is a constant second difference, which means I have a quadratic. Now we have one more to talk about. Now I have exponential tables. Remember, exponential has to do with that multiplication piece. So I have 5 halves and I'm going to take that and I'm going to move to 15 halves. Well, what is 5 halves to 15 halves? Right, I added 10 halves. So again, I'm on my first difference here. If I have 15 halves and I'm going to 45 halves, now I have 30 halves. And 45 to 135, correct, 90 halves. And 135 to 405, 270 halves. So That's not constant. And then I could go another one to check for my second difference, which would give me 20 halves, 60 halves, and then 180 halves. And if I'm looking there, that's still not it. So I know that it's not linear. I know that it's not quadratic, but I can look for multiplication. And one way that it might be easier for you to see that is if you turn those numbers, those fractions, into whole numbers. 10 divided by 2 is 5. 30 divided by 2 is 15. 90 divided by 2 is 45. And 270 divided by 2 is 135. Now, looking here, my first difference is not the same. And if I was to go to my second difference, I would say, well, 5 to 15, that's plus 10. And 15 to 45, that's plus 30. So I know that my second difference would not work for a quadratic. So linear is out, quadratic's out. But why does exponential work? An exponential is the answer because how could I consistently get from one to the next? How do I get from 5 to 15? I multiply by 3. How do I get from 15 to 45? I multiply by 3. 45 to 135, I multiply by 3. And that is the definition of an exponential function, is when we're multiplying instead of adding or subtracting. Okay, so when we are looking at a table to determine if it's linear, quadratic, or exponential, if the first difference is a constant for addition or subtraction, then we automatically know, yes, we have linear. If the second difference is a constant for addition or subtraction, we have quadratic. But if we see that we are multiplying to get from one term to the next, and we have a constant multiplication factor, then it is an exponential.